The next example is going to be using CUDA. It's going to be using GPUs, and I'm going to use that Titan Black that has great performance. For this one, we're going to be doing multivariate normals. And the reason why we're not just doing univariate normals is that it's really not any better. It's actually much slower than using the CPU if all I'm doing is generating a normal. But if I can also do my Cholesky factorization and the matrix multiply to get the multivariate normal, then we see benefits much more quickly. So it uses two libraries that are available in this CUDA toolkit, CURAND for generating random variables. And then actually this is not in the CUDA toolkit, but CULA is the LAPACK library. And this is, you just have to register on their website, and for academic use it's free. So if you want to play around with some GPU stuff, this is definitely something to look into also. So now, this is my initialization function for this example. This is a generator. I don't have to worry about multiple ones because it takes care of everything in the background, even though it's probably doing something similar. This is just for the matrix multiply functions. It needs a handle. This just needs to be passed to it. So these need to be global variables. I create the generator. This is the Mercian twister meant for GPUs. So it's almost the same as what we're using in the previous example. Set the seed. So that's going to be in this initialization function that I'll call from R. I'll pass it a seed. You need to initialize CULA to do any operation. If you don't do this, I forgot this before, it just gives you nonsense. It doesn't do anything, and then it took me a while to figure out why that wasn't working. And then I have to create this handle. These V2 are just for a different style of using the functions, but to do blast calls, you have to do this. And then I return nothing, because this really is just initializing things. And now this is the main part of the code. This will look, there's a lot of stuff going on here that's actually just setting things up to use it. I'm going to pass the number of multivariate normals I want, the dimension of them, and the matrix sigma, which I want to be its covariance matrix. Even though this is size t, you can use as.integer. It'll be coerced to the right thing, but wanted to make sure when I pass it to the functions later that they're really size t, very similar to integer, just very slight differences. These pointers are really going to be on the device is the GPU, and when everything that says device is really talking about GPU stuff. So I'm allocating room on the GPU for two matrices. One is going to be this covariance matrix on the GPU, and the other is going to be this dev data is really what I'm going to output things to. So this is going to really be a matrix. Matrices in C are just very long vectors. And they're done. One thing you need to, oh, this is important. BLAST is a Fortran library. Fortran is column oriented versus row oriented. And so you have to be careful when you're doing things in C, because C tends to do things by row. But these are really just two matrices on the GPU. I'm going to create my result, which is an R expression pointer, which is what I'm going to return. It's a matrix of size n by m. I'm also going to copy sigma, because this is going to change. I'm going to duplicate it and also protect it. Next, what I do is this host data. Host is the kind of terminology for the CPU. I'm going to get a pointer to my result. And this is really the matrix that's going to be passed in the end. Sigma is a pointer to the actual numeric part of this S expression vector. Alpha is just going to be needed for the matrix multiplication. It's just going to be a coefficient that's 1. I copy things over to the device. So I copy over sigma to dev sigma, and I'm doing host to device. So I'm copying this matrix, and then I'm going to do everything on the GPU. So this is now the main part of this function. This POTRF is really the Cholesky factorization in LAPACK language. And I'm using CULA on the device, and it's double precision, and it's Cholesky. This just tells it to store only the lower half. Cholesky is a triangular matrix factorization. So this only stores the lower half, and this just gives it the order of this matrix. So I Cholesky it, it stores it still in the same place. So it overwrites it before. So you have to be careful with some of these functions. Then I'm going to generate a bunch of standard normals, put them in dev data. Now this DTRMM is triangular matrix multiplication, matrix multiplication, and I'm doing it on the device. So I need to use this handle. These just tell it, I need to transpose things, tell it whether it's a lower triangular or upper triangular matrix. But the basic part of this is I'm doing 1.0 times my Cholesky factorization times the matrix of standard normals. And so this is a typical way of generating multivariate normals. And then all I do at the end, copy over the data on the device back to the host, free the memory that I've been using, and then unprotect the things that I created. And then I return the result. So the result has, the main part of it is this host data, is in the numeric part. So that numeric part is now a bunch of multivariate normals. And you need different flags to compile this. So instead of the LGSL flag, there's a whole bunch of CUDA flags and this CULA opaque flag. And so these, if you have any questions about compiling C code, you can let me know. I have a bunch of environmental variables set, so it knows where to look for these things. Otherwise, you need to tell your compiler where to look. And then in R, I can do a very, very similar call. I load my shared library, which was the output from here. I initialize, and then I call my function. I want, in my performance example, I'm gonna generate the same number of multivariate normals as the dimension that I'm in. So, you would need to, if sigma he would already set as some kind of covariance matrix, this would be the number that you want, and so this would output an n by n row of sigma matrix in R, and store it in A. And so, performance example, this one we get some huge speed up. Even if we're only in generating 10 10-dimensional multivariate normals, we're already half the time that it takes R MV norm. This is in the MVT norm package. This is what I had used for a long time. Even in 10 dimensions, we're twice as fast. By the time, if we're generating 10,000 dimensional normals, it's something like 20, 30 times as fast. And this can help a lot, especially when you want to deal with big data or problems. You really need to be able to do things in higher dimensions, and it can really take forever if you're doing things by default. And so this was my last example. I do want to say that I'm going to try to make the C code available. I'll give it to Justin, and he can post it online. And I hope that this gives you maybe some ways that you can think of speeding up R. R is pretty powerful. I also would say, for using R, I recommend that everyone at least start learning a low-level language, because R and Julia and all these things may die one day. They may not be there. C and Fortran are forever. No matter what, those will be around. Fortran's been around since the 60s. It's not going anywhere anytime fast. And no matter what new languages pop up, these will always be able to be interfaced with them. Anyway, thank you for listening. Thanks for coming.